So now with these numbers, the powers one, the exponents, there came uncertainty that whether these numbers are precise or not. We should also understand that there is a difference between precision and accuracy. So we go here for precision. Most of us are confused between them, but there is a clear difference between these two words. So basically precision is, let's talk in non-bookish language, then precision is suppose you take various readings for an experiment and you get different readings also. Obviously we'll get different readings as all the readings are exactly not same, because the normal machines that we use in common laboratories are not of so good that they get the most accurate, the most precise answer. Even I am also confused between precision and accuracy sometimes. But let's just clear it. Okay. So we are taking readings which are not exactly same because the machines are not so good. So precision refers to the closeness of these readings. The less difference between these readings, that means the more precise your instrument or your answer is. More precise means the less difference between various readings that you are taking in the experiment. Okay. So now when you get an experimental value, then you check it with the true value. Okay. So let's suppose that you are doing a practical exam. We do it correctly and submit our experimental value. Now our examiner and our teacher will be having a true value of the same experiment, obviously, to check our answer scripts. Okay. And he will mark us on how close our answer is to that true value. He will mark us on how close our answer, our experimental value is to that true experimental value which the teacher is having. Okay. So that this closeness is accuracy. How much accurate our answer is, how much close our answer is to the true value, how much close our value is to the true value. Okay. So once again, precision is how much, precision defines the closeness of various readings you are taking for the same experiment with the same instrument. That refers for precision. And accuracy means that how much the closeness of your experimental value with the true value. Okay. So those are two different terms. So now back to uncertainty, to find out the width of a staple pen with the help of a normal scale. Most of you try this. Just try to find out the width of a staple pen with a normal scale, that 15 centimeter one. Most of you will say it is coming out about 1 millimeter, but you won't be sure that the answer is accurate. You will be knowing that it is not exactly 1, but the closest reading is 1, so you are saying 1. Okay, so that unsurety, that is known as uncertainty. Okay, so that is uncertainty. In most of the questions, the uncertainty will be given to you, but if it is not given, so it is obvious to take uncertainty as plus minus 1 to the last digit. So now that's a new thing. Let's take that example only. So we were getting the answer for the staple pen as 0.1 centimeter. I can say 1 mm. So we were getting this answer, but we were not sure. So, and we don't even know how much uncertain we are. So we will simply take plus minus 1. We will take plus minus 1 to the last digit. So to the last digit, this means that this is the last digit. So after doing plus minus 1, we just need to say that the value, the actual answer lies between 0.0 to 0.2. Obviously centimeter. We need to say that this only. That because of uncertainty, and we don't know how much uncertain we are, so normally, normal cases where uncertainty is not given, we take it as plus minus 1. Similarly, in this case, minus 1 goes for 0 mm, to plus 1, 2 mm. So that's our answer. The true value will be lying between them. Or we can simply write that in this form also, that 1 mm plus minus 1. This is not correct, but basically this means the same, that 1 mm is our answer and plus minus 1 because we are not sure about that. Okay, so let's suppose that calculating a value of the volume of a liquid, we get, let's take an example, test value. So by doing so, while doing the, calculating the volume, we get an answer as 65.43 liters. We get this value of the volume of the liquid. So in this case, plus minus 1 will be done to the last digit, the 3, because this is the last digit we are able to see, the last digit of the number. Okay, so we will do plus minus 1 to the last digit, which means we are not sure, obviously we are not sure. So which means that the answer will be lying between 0.42 liters to 65.44 liters. So this means that the answer is between these two numbers. The true value of the answer is lying between these two numbers. Okay. So now, to handle with this problem of certainty and uncertainty, the concept of significant figures is launched. Okay. So let's just understand what are the rules for the significant figures and how to do this thing. Okay. Just to ease the certainty and uncertainty problems, we introduced significant figures. So now what we are doing is significant figures. This is a C. So we are now studying significant figures and the rules. The rules of the significant figures. So first one saying that all non-zero digits are significant figures. So suppose that we get a value of 253.85 kg. So there will be 5 significant figures, 1, 2, 3, 4, 5, as all non-zero terms are significant significant digits. Okay, so this was the first one. So now the second one says that zeros, all the zeros preceding to the first non-zero digit are not significant figures. Once again, okay, just try to understand that all the zeros preceding to the first non-zero digit are not significant figures. These only help into finding the decimal figure. So suppose that we have a very, very small number, say the mass of something goes for 0.0000085 kgs. So here the zeros preceding to the first non-zero the digit are not significant figures. Okay, which means that this whole number will be having 1, 2. So only 2 significant digits. These many zeros are only helping in finding out the decimal, how much small the value is in exponential things, not for significant figures. There are only 2 significant digits. Okay, just understand this. So now the third rule says that if there are 2 non-zero digits, let's suppose a number to be 314.00005 centimeter. Okay, so this is a number and there are zeros obviously here, and we have studied that we can, these are not significant, but these zeros are between 2 non-zero numbers. These many zeros are between 2 non-zero numbers. That means this 5 and this 4. These zeros are between 4 and 5. So if there are zeros between 2 non-zero digits, then these zeros are considered to be significant. Okay, so the number of significant digits here is 1, 2, 3, 4, 5, 6, 7, 8. So our answer of number of significant digits is 8. Okay, so between two non-zero digits, if there are zeros present, they are considered to be significant. Moving on next. Now zeros to the right of the number are significant if and only if they are on the right side of the decimal point. Okay, so this was a bit confusing, so let's take it into normal language, which means that if the zeros end before the decimal point, those zeros will not be considered as significant. Now you got it? Okay, the zeros that end before the before the decimal point will not be considered as significant digits. So suppose that we have a reading as 881,000. Okay, we have a number this. So there is no decimal point. This means that whole number is to the left of the decimal point. So we will not consider these three zeros because and they end before the decimal point, so will not be considered. So 1, 2 and 3. We get 3. But if there is a number like 881,000.0, we will consider the digits. Okay, because the decimal point is lying between here. The number is not ending. The number is not ending before the decimal point. It is ending after the decimal point. The decimal point is coming in the number. So we will consider all the zeros here. 1, 2, 3, 4, 5, 6, 7. So the number of significant digits goes for 7. It is not that difficult to understand. Just it's simple things. Just pay some kind of attention. Attention is obviously required to get anything. Just to understand things, attention is definitely required. So, and one last thing, like counting objects. Like you're counting, there are 3 balls, 20 glasses, 5 switches, 8 pencils. So these things, like I was saying, 3 balls. So this is a whole number, and you are counting the balls 1, 2, and 3. Suppose I have 2 markers, the 2 whiteboard markers. So I'll write 2 markers here. I am counting these 2. Okay, so that means I am definitely sure about there are only 2 because I have counted. So this means that there are infinitely many number of significant figures in these. 3 balls. We are definitely sure that there are 3 balls because we have counted them. So this means the number of significant digits here goes for infinity. A very, very, very large number. Okay. So basically these are the significant figures and the rules which describe them. And that's it.